how to calculate partial derivatives. First, let's define the partial derivatives. So we take a function f of two variables defined on a domain omega and R2 into R, and a point A, A1, A2 in the domain of definition of f. Now, the first derivative of f with respect to x at the point A1, A2 is defined as being the rate of change of the function f in the direction x. So the definition will be similar to the definition in the one variable case. It's the limit when h goes to 0 of f of a1 plus h a2 minus f of a1 a2 over h. So it's the rate of change in the direction of the first variable at the point a1 a2, and it's denoted df over dx with a rounded d, because we would like to insist on the fact that it's a partial derivative, so it's a derivative with respect to one variable and we have other variables in the expression of f. In the same way, we define the first derivative of f with respect to y, the second variable, at the point a1, a2, as being the rate of change as well. So it's the limit of f of a1, a2 plus h, so the h now goes to the second variable. It's the rate of change with respect or in the direction of the second variable minus f of a1, a2 over h, and it's denoted df over dy at the point a1, a2. So it's the rate of change, so somehow it's the slope. It's the slope of a tangent. So geometrically speaking or graphically speaking, the existence of the two partial derivatives with respect to x and y, of course, is equivalent to the existence of two tangents in two directions, so the x direction and the y direction. So if these two tangents exist in these two directions, then the partial derivatives exist. Let me open two brackets here to insist on one thing. In fact, the existence of two tangents in two directions, or the existence of the partial derivatives of the function f at the point a1, a2, is not enough to say that the function f is what we call differentiable at this point. So for the function f to be differentiable, we should have more conditions. In fact, the existence of two tangent lines in two different directions is not enough. The existence of tangent lines in any direction is not even enough. For the function f to be differentiable, we should have tangents in any direction, and all these tangents should be in the same plane, should belong to the same plane. So for the function f to be differentiable, we should have the existence of a tangent plane at the point a1, a2. In practice, how do we calculate the partial derivatives? Let's take a first example. F of xy equals x2 plus x sine y. First, we should check the domain of definition. This function is defined at any point xy in R2. Moreover, since it's a polynomial and a sine function, so it's differentiable even at any point in R2. So we can calculate the partial derivatives at any point, of course. So to start, the first partial derivative, it's df over dx at the point xy, should be calculated by considering that y is a constant. So we look at the function as if y was a constant, and we calculate the derivative using the formulas you already know for the one variable case with respect to x. So the derivative of the first term x2 will be 2x, and for the second term x sine y will be only sine y, because it's like a constant multiplied by x. Same, we do the derivative with respect to y. So the first term x2 its derivative will be 0 because it's a constant with respect to y, and the second term x sine y, if we consider that x is a constant and sine y is like the function to be differentiated with respect to y, so we keep x and the derivative of sine y will be cosine x. We keep x, of course, because it's multiplied, like the case when you have like derivative of 5x, it will be only 5, you keep 5, or the derivative of 5 sine x, it will be 5 cosine x. Let's take another example. F of xy equals ln xy squared plus x2 exponential y. So this function is defined continuous at any point in its domain of definition, not any point in R2, because in this case x should be positive and y should not be equal to 0 for this function to be defined. So we will calculate the derivative at one of these points. So df over dx at xy will be, if you look at ln of xy squared, you consider that y is a constant. So ln of the derivative of ln of xy squared will be the derivative of what's inside xy squared, so which is y squared, divided by xy squared, the whole function inside ln. So the derivative will be y squared over xy squared, plus then the derivative of x2 ey. If y is a constant, so the derivative will be only 2x times the constant ey. We do the same thing for df over dy, and we can simplify, of course, both expressions. Now we can go even further and calculate the second derivative. So it will be denoted by d2f over dx2, and that's equal to the derivative of the first one. So the derivative of 1 over x in this case will be minus 1 over x2 with respect to x, of course, and the derivative of 2x ey will be 2ey. We can calculate the second derivative, in fact, of df over dx with respect to x or to y, and also the derivative of df over dy with respect to x or to y. So we have 4 second order derivatives. So df over dx2 will be minus 1 over x2 plus 2ey. Then we can calculate what we call d2f over dx dy. So it's the second derivative with respect to x then to y. It will be 2x ey, because 1 over x, the first term, is a constant with respect to y, and the second one, 2x, is a constant, and the derivative of ey with respect to y is ey. We can also calculate d2f over dy2 and d2f over dy dx, of course. Then if we look closer, d2f over dx dy and d2f over dy dx have the same expression. In fact, this is the Schwarz theorem. The Schwarz theorem says that if you calculate the mixed derivative with respect to x and to y, or with respect to y then to x, and if your function has some irregularity, like it's C2 is being differentiable and having all the derivatives continuous to the order 2, then the mixed derivatives will be equal.